Hello again. So far what we have done is to get an energy minimized configuration for liquid argon. Is that the em.gro file?
Yes.
Yeah. So please continue.
So we will now use the em.gro file, that is the energy minimized configuration, to run our full molecular dynamics simulation so that we can get the trajectory file out of it. So we'll again generate the TPR file using the command growmpp. So we'll type growmpp minus f full.mdp, which is the molecular dynamics parameter file for the full molecular dynamics simulation. Then minus c em.gro. Em.gro is the energy minimized configuration for liquid argon. Then minus p topol.top.
That is the same as before.
Yeah, that is the same as before.
And what are the differences in full.mdp and em.mdp?
In em.mdp, we are not specifying that whether we need to keep the temperature or pressure constant or not. We are not specifying that after how many steps we are going to save the trajectory file or the coordinate or the velocities. What is the way by which we are generating the velocities, or in case
so
of...
for energy minimization, we don't need any velocity
No,
or anything.
we don't need. Then
Okay.
we are even not, in case of polyatomic molecules, we'll be using algorithm to fix the bond length and bond
Correct,
angle.
correct,
So
right.
all these parameters will be using in the full
Full
dot
MDP,
MDP and not
right.
in the energy
Right.
em.mdp
Okay.
file. And then we'll get an output file minus o full.tpr minus max1 space 2. So here the output file we are getting is full.tpr. And now we'll run this full.tpr using the command mdrun to get the trajectory.
So again, when you say DEF, FNM, that means all of them will have the same
initial full, and
right.
then we'll get files
right.
full.gro, which will be the gro file after full MD simulation, then full.trr, full.edr, full.xtc. So all will
instead
have
of full, it can be any other name also.
No, but then you have to have the TPR file in that name, because since we the TPR file, that is the output file of growmpp, is full.tpr.
Okay.
So we are giving minus DEFFNM space full. If you give their em.tpr, you have to use em, or if you give their growmpp.tpr, you have to use growmpp instead of full. So that two names have to be similar.
Okay.
So now since we have all the trajectory file,
so this whole information is contained in the TPR file.
Yes.
And I can view it. What is the command to view?
GMX dump.
So I can dump and view the full TPR file.
Yes.
But this is usually a very large file.
Yeah, this is this contain all the information in the GRO file, top file, and MDP file.
No, in fact, I would recommend to all users that once in a while check the sizes of the files, because if the files are too much, I think it can it not fill the whole hard disk?
Yeah, it can fill the whole hard disk. It
Right.
depends on the size of the system.
Correct.
Suppose you have a file, you create a box which have 1 million atoms, then it will have a large TPR file.
So it is a good idea every now and then to take all the files from your computer disk and to put on a separate external hard disk.
Yeah.
Because otherwise, the first time we ran the program, the student gave 50 million steps because he wanted to do a very large simulation. Then the whole hard disk was full and we had to call the expert to really restart the whole thing. So be careful about the file sizes and keep monitoring it all the time. Yeah, proceed.
So after we get the full.xtc, TPR and all files, so now we'll analyze the trajectory, that is we'll calculate some properties.
So whatever the present simulation were done, were they NPT or NVT?
They were NPT.
Okay, so it's a constant number, constant pressure, constant temperature. Okay.
So we'll first calculate the radial distribution function between two argon atoms. So to calculate, we have to first create...
what are the different types of analysis available? One is your radial distribution function.
Then you can calculate diffusion coefficient.
Correct.
You can calculate the distribution of bond angle, dihedral angle. Then you can calculate the spatial density map.
Okay.
Then you can calculate the angular distribution function.
Different types of correlation functions.
Different type of correlation function, hydrogen bond.
So is there a list of all the analysis I can do?
Yeah. There is, when you install GROMACS, it will have a bin folder.
Okay.
And in that bin folder, you will have a detailed list of commands, which are the command that is
for analysis. Okay.
There, all the commands are given.
Okay.
Starting from creating a topology file, that is PDB to GMX, to all the commands.
Once you have hydrogen bonded molecules, you can calculate the hydrogen bond lengths, hydrogen bond distribution.
Yeah, the energy of hydrogen bond, correlation function involved in there.
So can you calculate the say average energy between two specific groups during the
Yeah,
simulation?
then you have to create two specific group using
Okay.
this index. You have to create an index file for
Okay.
specifying those two specific groups between which you want to calculate the interaction or hydrogen bond. So
So suppose you want just the Coulombic interaction between two objects as
yeah,
a
then
function
you
of
have
time.
to specify that between which two object you want the Coulombic
Right.
interaction. That you have to specify in the MDP file.
Okay.
In full.mdp, you have to type an extra line energy groups.
So a lot of options are there. What we can do on the website, we can give a list of all the things that can do,
Yeah.
and maybe even store a set of results so that people can use it
Yeah.
and test their skills.
Yeah, sure.
Okay? Yeah.
So to calculate radial distribution function between two argon atoms, we need to first create an index file. So we can create an index file using the command make underscore ndx. So what we need as an input here is just the GRO file. So make underscore ndx minus f conf.gro minus o, which is the output file, index.ndx. Then when we type enter, then we'll have to type q is save and exit, and then again enter. So it will create an index file.
Can you view this index file using
Yeah,
VI?
we can view this index file using vi command.
Okay.
So now to calculate the radial distribution function, we have to type the command g underscore rdf. rdf is radial distribution function. Space minus n index.ndx space minus f full.xtc. xtc is the trajectory file. Then space minus s full.tpr. Then space minus o is the output file, rdf.xvg. So whenever we want to analyze any file or we want to calculate any property, there are three files that is needed. The first is the ndx file, that is the index.ndx. Then is the xtc file, that is the trajectory file, and then is the tpr file. These are the three files that is required for any kind of calculation, any kind of analysis.
TPR file doesn't include some information of trajectory?
No, TPR file doesn't include. TPR file include information about the topology file, about the GRO file,
Okay.
and about the MDP file, but it doesn't include any information regarding the trajectory. All information regarding trajectory is contained in the XTC file.
Okay.
So there is the command. So after we type this command, it will ask us to select a group. So first we have to type 2 and then enter. So it will show something like this, that select a group.
Okay.
So you type 2 and then type enter, and then again you type 2 because it is between two atoms, radial distribution function. So you have to select two groups, and then the file is created as rdf.xvg, and then if
No,
we
no, see,
yeah.
the radial distribution function is between pair of atoms,
Yeah.
right? So don't you have to give pair there?
Yeah, so it will take first, it will take, when we type 2, it will
Right.
take argon atom, and
Okay.
then again if we type 2, then it will again take second argon atom. So it will calculate between two argon atoms.
But there I have C 1 and 2, no, on the left.
1 and 2?
See in that file,
Yeah.
there is 0, 1, 2.
Yeah, 0, 1, 2, since it's a monoatomic molecule and it's the same molecule, so it doesn't matter 0 system, you can as well select 0, 0 or 0, 1 or 0, 2 because all of them contain argon atom only. But
Okay.
when we'll have polyatomic or triatomic system like water or CO2, there we'll have three different sites. So we have to create index file for, in case of water, say for oxygen. Then for, there are two hydrogens, so we have to create an index file for two different hydrogen.
So instead of 1, 2, can I give 1, 3?
But there is no 3 in this case, so you cannot give 1, 3 because it is 0, 1 and 2, right? So
Okay.
you can either give 0, 0, 0, 1, 0, 2, 1, 1, 1, 0, 1, 2 or 2, 0, 2, 1, 2, 2.
Because everything is?
Everything is same here because
Okay.
it's a monoatomic molecule.
Okay.
But in case of triatomic or polyatomic molecule, we have to specify between which atom. Like we have to create
Okay.
index file
Yeah,
for each of
yeah.
them. So rdf.xvg file is created.
So when
and
you give in that XVG file, it is a correlation function between argon atoms.
yeah, it is a
Does it average over all the 547?
yeah, it is averaged over all the atoms.
567 or 47?
567.
Okay.
So now we'll display the graph in XMGrace. So, and XMGrace is a plotting software. It's also free software. So we just type XMGrace rdf.xvg. It will display this graph between two argon atoms. This is the radial distribution function plot, where the x-axis is the distance between two argon atoms in nanometer, and y-axis is the radial distribution function.
So that XMGrace already knows what to labels to give?
Yeah,
Huh?
it will put the labels.
In nanometer, and
Yeah,
Right?
it will put the labels.
because that must be already contained in that XVG file, no?
Yeah, in XVG file it's written that something there is distance and then there is the value of radial distribution function.
So XVG file can be edited, like
Yeah, it can be edited. After
okay.
it is created, you can edit it.
Okay.
And then it will plot it accordingly
Okay.
in assemblies.
So if you want to view actual numbers, you can go to that XVG file and
You
see those
can
numbers.
go via rdf.xvg and then you can open the file and then you can view the file.
See, for example, on the GFR,
Yeah.
I see that there is a minimum around less.
Less than 1 nanometer.
Right, so I think it is around say
0.65
0.65 or something.
yeah.
So from the graph you may not be able to read. So you go to that XVG file,
Yeah.
edit it, and you will know exactly what is the value of the minimum.
Where the minimum is or what is the value is.
Okay. So this RDF.xvg contains only information about RDF.
Yeah.
Okay, so what are the next things we have
So
here?
now, if you want to calculate diffusion coefficient of argon atom,
Okay,
so with the help of this G underscore MSD, MSD is the mean square displacement.
okay,
So you can calculate the diffusion coefficient of argon. So here also we need 3 input file and the input file is same, that is index.ndx, full.xtc
and
and full.dpr, and then minus O diffusion.xvg.
Okay,
So if we just type it here also, again it will ask to select a group, right, for which atom or for which group we want to calculate the diffusion coefficient. Since here 0, 1, 2, all these three contain same information, so we'll just type 2.
so it could have been 0, 1, 1.
No, here we just have to type one group or one, because
Okay.
we are calculating diffusion coefficient,
Okay.
not between two atoms, it's just one atom or
Right.
one molecule ka diffusion. So after we type 2 or 0 or 1, something like this will be displayed in the screen. So here we'll have the value of diffusion coefficient as 12.2337.
Okay,
Within bracket is the error bar and then into 10 raised to the power minus 5 centimeter square per second. So here it is being calculated using the Einstein's diffusion coefficient formula. We can as well calculate diffusion from velocity autocorrelation function
now
also.
suppose I wanted the plot of mean square displacement versus time.
So you just type xmgrace MSD or diffusion.xvg.
Okay.
So it will give a graph plot passing through the origin. We'll
Okay.
see it when we perform the simulation on screen
Fine,
here.
fine. Okay,
So
so now this is about the diffusion constant.
yes,
Now since we have some time, why don't we just discuss the installation a little bit?
yeah, sure,
So installation usually you can do in about 15-20 minutes
yeah.
if everything goes well. If something doesn't go well, are there some help sites where people can approach?
Yeah, there is Gromax installation site, which is a
Okay.
free site where
Yeah.
people do ask question about if they have difficulty in installation and all.
Okay, and you can always send a mail to us if you are stuck. The
Yeah.
students can send us a mail.
Sure.
Okay, so we'll now discuss quickly Gromax installation. This is just a discussion. We'll actually show the installation in 1 or 2
Yeah.
lectures. Yeah.
So to install Gromax, Gromax is basically a free software which can be downloaded from the website given here, gromax.org. So when you go there, there will be different version of Gromax available. So download the latest version as a tar file, and to install Gromax,
No, go back.
yeah,
So you can do that in Windows also.
yeah, we can do it in Windows also. But Windows is a paid software, right?
Correct,
But Linux is free.
Right.
So
But what is the kind of minimum RAM that is needed roughly? Suppose I have a 4 GB RAM, is that enough?
4
For-
GB, I guess more than that is required, because just installation is not enough. When you install it, you
Right.
might as well want to perform simulation.
Correct.
And so there the file will be very large in size. So
So-
I guess,
Minimum 8 GB.
yeah, 8
Huh?
GB is fine.
Okay. So Linux is easiest because,
It's a free software.
and plus also, I think in Linux the entire memory will be available.
Yeah,
Whereas
That's
in
true.
Windows, the Windows itself will take a huge
take
space.
huge space.
Correct? Okay.
So to install Gromax in your machine, there are 3 things that is required. So first you have to have a compiler, that is G++ compiler. Then we have to have a CMake, and we have to have a FFTW also. So all these are free and it can be downloaded from the website link that is given in the slide. So first we'll have to install the compiler in the, say in Ubuntu. So to install it, just type the command sudo space app minus get space install G++ 4.7, it will automatically get installed in your PC.
So after G++, is there a minus sign there?
Yeah, minus 4.7, it's a version.
Okay.
It's the latest version now.
So that
You
what?
have to type it, first you log into your remote machine and then you go to terminal
Okay.
in Ubuntu and then you just type sudo space apt minus get space install space G++ minus 4.7.
So what will this install?
It will install the compiler G++.
Okay.
So after this,
But is it possible that Linux itself has a G++?
yeah, it's possible that Linux, if it already has G++, it will just show that the latest version is already installed.
Okay.
It will give the command.
But if you do it, will it reinstall on top of the old one or?
Yeah, it will reinstall.
Okay.
If an older version is installed, it will
Okay.
reinstall an
Okay.
updated version.
Okay. And the next one is what?
Next one, it will just update all the software that is installed.
Okay.
So now to install CMake in Ubuntu, so first you have to download it from cmake.org. It's a
Okay.
free site, free software. You can download it, the tar file, and then you untar the tar file using tar space minus xvzf space CMake, whichever version is available, but preferred is the latest version.
Okay.
Then you go to the directory cd space CMake. Then there will be a file named configure. So you have to configure it using the command /configure. After the configuration is successfully done, then you have to type the command make space minus j6. So it will make the file and then sudo make install. It will install CMake. So these are the 4 steps.
So all these are just to install the CMake, which is needed later.
And same command you have to type to install FFTW as well.
Okay.
So you install FFTW from the site ffTW.org. It is also a free site.
Okay.
And then you will download the tar file and you have to untar it using the same tar minus xvzf command.
Okay.
Then you go to the directory FFTW, then you configure it, then you make and then make install. So same as CMake.
So in which directory does it install?
So wherever you download the CMake, FFTW and Gromax, all these 3 have to be in a same directory. Suppose it's in, initially when you download it, it will go in a download folder.
Okay.
So you go to cd space download
Okay.
and then you first unpack CMake, then you unpack FFTW there and then you install Gromax in the same folder because all 3 CMake, FFTW and Gromax have to be in the same directory.
Okay. So what is the typical name that you want to give to that directory?
It's user defined.
Okay.
Anything.
So what do? You give just Gromax as the directory?
Yeah, I just give Gromax as the directory.
Okay.
So then you install FFTW using this command. It is the same as CMake.
Okay.
And then to install Gromax, you will also have a tar file there.
Okay.
So you just unpack it using the command tar space minus xvzf space Gromax.
So what do this xvzf do?
It unpacks the tar file.
Okay.
Then you go to the directory using cd space Gromax. Then you have to create a directory named build. So
But have we created Gromax directory to begin with?
no, we have not created.
Ah.
We can create cd Gromax and then
Okay.
we can have all these 3 files in that Gromax directory and then we can one by one start installing
Okay.
it.
Right.
So then you have to create a directory called build. So typing the command mkdir. So when you
this build will be a subdirectory of Gromax.
yeah, it will be a subdirectory of Gromax. Then you go to the directory cd build
Okay.
and then you have to type the command cmake space and then wherever your Gromax is downloaded,
Okay.
you just drag the folder. It will automatically give the path.
So that Gromax minus 5.1.4, is it an untarred file already?
Yeah, it's a folder.
Okay.
So wherever it is downloaded,
Right.
so you just have to drag the folder there. It will automatically give the path. Suppose in my case, it was downloaded in home, then Sonanki, then downloads, and then there was the Gromax directory. So this was the folder
Okay.
where it was downloaded. And then you have to type space minus all in caps dgmx underscore build underscore own underscore ffTW is equal to on.
Mhm.
So after this, it will take 2 or 3 minutes to install Gromax.
Okay.
Then you have to type make space minus j6 and then sudo make install. And after the installation is done properly, we just type source user local Gromax bin gm xrc. So in this bin directory, you will have all the commands.
Okay.
So to ensure or make sure that Gromax is installed properly or not, you can type any command to just check. If it is installed properly, it will give you a list of things. Like if you type grow MPP, it will write that, okay, this is the input file option, this is the output file option. But if it is not installed properly, it will show nothing.
Okay.
It will say this is not installed here. Please type other thing to view.
So how many more things are there? Is it complete now or you
Yeah,
have more?
Gromax installation is done.
Yeah,
So
so
it just
now-
take 10 to 15 minutes to install it.
So now if somebody asks a question, why I should spend these 15 minutes, what is your response?
If you want to use Gromax, you have to spend this 15 minutes, and it's a very free software. It's fast. You can simulate large number of molecules. in this.
So what I would like to say is that you can calculate all the equilibrium and dynamic properties of
Any
liquids
system.
and mixtures
Yeah.
and ionic solutions.
Yes.
Literally you can do most of thermodynamics and a large part of kinetics in solution media,
Yes.
except chemical reactions.
Yeah.
Okay, so for example, people learn about free energy, people learn about entropy.
Yeah.
These are all objects which we hear and we don't have what the actual values are for a given system. See, for example, we want to do simulation on water. So I want to calculate, let us say I want to calculate the heat capacity of water.
Yeah.
Can I use Gromax to do that?
Yeah. We can calculate heat capacity using Gromax.
Okay. So the way I would do heat capacity is the rate of change of energy with temperature.
Yes.
Correct? So what I would do, suppose I want heat capacity at 298 Kelvin.
Yeah.
So I would calculate the average energy of the system at 298
And
and
as a
energy
function,
at say 296, then 300. So
as a
if I
function of temperature.
if I have energy as a function of temperature, I can take the derivative and get heat capacity.
Heat capacity. Yeah.
So I can get heat capacity at constant pressure
Yeah.
as well as heat capacity at constant
Volume.
volumes, because CV and CP are different.
Yeah.
So I can do simulation at constant volume, which is NVT,
Yeah.
to get CV.
Yeah.
I can do at constant
Pressure.
pressure, which is NPT. So I can do this.
Yes.
Okay. So for example, now we want to know, let us say, the average number of hydrogen bonds between each water molecule in a liquid.
Yeah.
So how would you do that?
G_H bond.
Okay, so that is part of your list of.
List of commands here.
Okay.
It calculates and it uses the geometric definition, which is already installed. It will take the minimum distance angle criteria to calculate.
So now suppose I want to change those parameters.
So you specify the bond angle and you specify the bond length. You can do that as well.
So if the software has its own definition, I can give a different definition.
You can give a different definition of your own choice.
Suppose I have OHO bond. Typically we take 30 degrees
Yeah.
as the bond angle.
Yes.
But I want to give it 40 degrees to
Yeah,
see whether.
you can use it.
Right?
You can change it.
Okay, so to summarize what we have done so far, what we did was we gave all the files that were needed in the Gromax software, okay, and gave two examples of execution. One was to calculate the pair distribution function, and another was to calculate the diffusion constant. Of course, we did not plot the curve for diffusion constant, but that is very easy using your
XMGrace.
XMGrace.
And we'll show it.
Okay,
also.
so then we gave basic installation commands in Gromax. So you have already seen the commands. After 1 or 2 lectures where we consider water and one mixture, so let us see what these commands are, and once we are familiar with the commands, we will start the installation procedure. So that when we start installing, then you already know what commands that have gone into that, and you will get a much better feel. So that we will do after 1 or 2 lectures. Today we will just conclude here, where we have given basic commands for installation. And are there some manuals where these are available?
Yeah, for each version of Gromax,
Okay.
there are manual available and it can be downloaded. It's free of cost.
So, okay, one good idea would be whatever we are giving here in a few lectures is a very small subset of the whole thing that is available. So, I would recommend to users just start reading the manual, because in many of these manuals, lot of theory is also given,
Yeah.
right?
Each algorithm is
Like
described
when we
in
discussed
detail.
specific algorithm, for example, what is that evolved sum, what is a particle mesh evolved, what are all these potentials, what are all these parameters. So it's a good idea to look at the manual as well. So when we do some actual calculations and do the analysis, we will also tell you what these things mean, but it will give you, it is an investment, and whatever work you do in the future, all of this thermodynamics and kinetics will be actually possible to verify this by yourself. So that is the great advantage of this, very, very powerful. So if you know how to use Scilab well and how to use GROMACS very well, there are many, many things what you learned in school or college, you can actually verify in your calculations. So we will conclude this lecture here and continue with water next time. What do we want to do?
Water and mixture.
Simulating water and simulating a mixture. That's what we will do next time. So we will conclude here. Thank you.